So, let us continue our discussion on linear first order autonomous systems that we defined in the previous lecture. So, what we will do today is we will formally define what is called the phase portrait of a system. Okay. So, the simplest example of the first order system which is linear and autonomous was what we took up in the previous lecture. So, linear first order autonomous system. The simplest example for this would be dx by dt is equal to a x, and we saw that in fact for a liquid level problem, this is one of the cases where you do not have any input to the system and the valve that you use at the outlet works such that the output flow rate, volumetric flow rate is constant times the level of the liquid in the tank. So, now we would like to understand the dynamical behavior of the systems which are of this particular form. Okay. So, let us first try to understand the meaning of this equation. The meaning of this equation is that the rate or time rate of change of the dynamical variable is a function of the dynamical variable only. Okay. So, dx by dt, which is the time rate of change, is a function of the dynamical variable only. Okay. And what kind of a function? Since this is a linear system, in this particular case we are considering simply dx by dt is equal to a x. Now, a simple question which may arise is that how many equations are these? So, if I write this as dx by dt is equal to a x, how many equations are currently under consideration? By looking at it, the answer may be very trivially that there is only one equation, but we have actually not defined what is the value of a. So, if dx by dt is equal to a x and a is equal to 1, then you have the equation dx by dt is equal to x, and when dx by dt is equal to a x where a is equal to minus 1, then the answer is, then the equation is dx by dt is equal to minus x. So, therefore, these are two equations, right. These are two equations for two different values of a, and therefore, the behavior of the system would actually depend upon the value of a here. This is an important parameter. This is an important parameter associated with the system. The number of equations which you actually have is very many, and if in your case a belongs to R, then you in principle have infinite number of such equations, because you have infinite number of a's, and therefore, one needs to understand the dependence of the dynamics of the system on the value of a, or the nature of a rather. Okay. So, therefore, let us look into the solutions and the behavior of the solutions. Our equation is dx by dt is equal to a x. Well, it is not very difficult to see that the solution for this problem is that x of t is equal to x 0 e to the power a t, where x 0 is the initial condition. In fact, this is an initial value problem, dx by dt mathematically is an initial value problem, and therefore, to solve the problem you need to specify the initial condition. So, x 0 is the initial condition. So, given an initial condition, which means that if I know this is t and this is x, at time t is equal to 0, if I know the value of my variable, this is x 0, then what is the information that I get from this equation, from equation 1? Equation 1 gives me the derivative, this is the derivative. Okay. So, I can determine dx by dt at t is equal to 0, which will be equal to a of x 0, and x 0 is known. So, therefore, my derivative is known. So, now I have the initial point and I know from the derivative the direction in which I need to proceed. I know the direction. So, it is very simple, I know where I am and I know the direction in which I need to go. So, therefore, I can know the future of my system. I can know the future, or in certain sense the fate also of my system. Okay. So, if I know the initial condition and I know the derivative using this initial value problem, I can know the future or the fate of the system. Okay. So, now when my solution is x of t is x 0 e to the power by a t, what is the meaning of this? Well, x 0 is a constant, x 0 is a constant, but the dependence of x of t on time is coming from this exponential function. Exponential function. Okay. So, we although know how does the exponential function behave, still let us look into the behavior of an exponential function using an online utility. This is called Desmos calculator. So, this is an excellent utility. I would encourage you to visit www.desmos.com/calculator, the URL which you can see here. Here the URL is visible. Okay. And this is a free tool and it has really wonderful features, and throughout this course we would be using this particular online suite for visualization of different dynamics which is associated with the system. Okay. So, let us see what we will do is we will try to punch in an exponential function. So, f of x is equal to my initial condition, say x 0 to exponential of a x. Now, this particular software takes x as the variable, whereas in our analysis t is the variable, because we are considering dynamical systems, we are considering engineering systems, and therefore, we would be using t, but whenever we have to visualize our dynamics using this software, it would be inevitable to use x as the independent variable. So, please remember that x in this case is nothing but time. So, let us see how does the system behave. So, let me have a look into the solution behavior. First of all, let us look into the effect of initial condition. Okay. So, as I change the, you can see here 0 1, which means at time t is equal to 0 the value of x is 1. As I increase this to 2 or say 3 here, the variable goes from 0 1 to 0 3. So, I can animate it and you will see if I have to see only the effect of the initial conditions, which means I focus only on the y intercept, then what I see is that as I change the initial condition, the y intercept is changing. Okay, fine. So, I will fixate some value of initial condition, say I will fixate it on 2. Okay. Now, for a is equal to 1, which means a is greater than 0, I see an increase in the value of. So, see the time t is equal to 0 starts from here. Okay. So, for engineering applications, this negative part of the time does not exist. For the sake of mathematical completeness, we can always analyze the problem for negative time as well. So, if I start the analysis from here, this is how my dynamics looks like, that I start from the initial condition, which in this case is 0 2, which is in this case is 0 2, and the value of my variable keeps on increasing to what extent? In fact, it never stops, it goes to infinity. Okay. The value of my variable goes to infinity when the value of a is 1, and in fact, I can further increase, and you will see that as I increase the value of a, the rise is much steeper. Okay. So, I can limit say this value from minus 1 to 1 and try to see the dynamics. What I see is that in all the cases, as long as the value of my variable is value of my parameter a is positive, your system always blows up to infinity. The value of the dynamical variable goes to infinity. But then a strange thing happens, that the moment I make it negative, when I make my parameter a negative, what happens is that my system actually goes from the initial condition to 0. Okay. And if I confine the values to only negative and animate it, what you will see is that irrespective of the value of a. So, these are two important things. When a is negative, irrespective of the magnitude of a, as time t tends to infinity, the value of your dynamical variable always goes to infinity. So, let us see here, the value of your dynamical variable here has gone to infinity. I can reduce the value of a, and you will see that whatever may the value of a be, at time t tends to, as time t tends to infinity, your value of the variable dynamical variable goes to 0, and completely opposite would be the case when you have positive value of a, irrespective of the magnitude of a, your value of the dynamical variable always blows to infinity. Whatever you do, if a is positive, your value of the dynamical variable goes to infinity. So, now we see an interesting thing, that I have now x of t is equal to x of 0 e to the power a t, right. This is the solution, but what happens to this the solution as time t tends to infinity? X of t tends to 0 when a is less than 0, and x of t tends to infinity when a is greater than 0. And then I see one more thing here, if a is equal to 0, let me set a is equal to 0. You see here, there does not occur any change in the variable. So, therefore, when a is in fact equal to 0, x of t will be x of 0 when a is equal to 0. Whatever may your initial condition be, the system will remain at that condition. Okay. So, can I draw the general behavior of my system in this case? So, the answer is yes, and that is what is called the phase portrait. Phase portrait. So, phase portrait of dx by dt is equal to ax. Okay. So, let me draw the axis first. As I said, for your specific problems, the t can be only positive, the value of the variables can be confined to some specific value, but for the sake of mathematical completeness, let us look into all the possibilities which the system can sample. So, I have time t here and I have x here. So, when a is greater than 0, when a is greater than 0, what is going to happen? You may have some initial condition and the system will blow to infinity, and when you go as time goes to negative, what you will see is that asymptotically the system goes to 0 in the negative direction. Okay. Similarly, for different values of initial conditions, you can draw different possibilities. So, these are different initial values and you can draw it for various values of a, but the condition is that in all the cases a has to be greater than 0. When a is less than 0, so let me draw the axis again. This is t, this is x. For a less than 0, when a is less than 0, if you start with a particular initial condition, then what is going to happen is that you will exponentially go to, this will go to 0 to 0, okay, and this, all of this will tend to 0 with different initial conditions, with different initial conditions. So, what do you see here? What you see here is that you have one phase portrait for a greater than 0, you have another phase portrait for a less than 0, and when a is greater than 0, the dynamical variable tends to infinity, and when you have a less than 0, the dynamical variable asymptotically goes to 0, which means what? Which means that the fate. So, as time t tends to 0, time t tends to infinity is the fate of your system. What is going to happen to your system at longer times? Say you do not have any control system implemented in your system, then what do I expect? Imagine that you have a reactor and you want to control its temperature. So, my question is that if for some reason that control system fails, or for some reason there is no control system at all, then what is going to happen to the temperature? Is the temperature going to blow up to infinity, or the system is going to cool down to 0? Infinity in this particular example would be very high temperature, such that the system fails mechanically, and 0 in this case would correspond to say the room temperature. Okay. So, these are the two extremes in which under normal circumstances you can expect the system to have to sample the different variables. Okay. So, the question would be that if I leave the system and let it evolve in time, then what is going to happen to the fate of the system. And so, if you have an autonomous system, then if A is greater than 0, then you can expect an indefinite increase in the value of the dynamical variable. Whereas, if you have the value, if you have the variable A which is less than, or the parameter A which is less than 0, then you will see that you in fact will encounter a situation where the value of the dynamical variable will become 0. And these are two very contrasting situations. On one hand, the variable tends to infinity, on the other hand the variable tends to 0, and therefore, the system is said to have bifurcation. So, we say that the system has a bifurcation. Okay. So, let us see what is our system. Our system is dx by dt is equal to a x, right. For a greater than 0, limit x t, t tends to infinity, and for a less than 0, limit t tends to infinity, x t is in fact 0. So, therefore, the system has a bifurcation at a is equal to 0. The system has a bifurcation at a is equal to 0. Then we need to introduce a concept called equilibrium solution. Okay. So, equilibrium solution is a solution at which the gradients in the system become 0. So, if dx by dt is equal to a x, then we determine the equilibrium solution by setting up dx by dt at x equilibrium is equal to 0, which means a x is equal to 0, which means that x e is equal to 0, which means that x is equal to 0 is an equilibrium solution, and the meaning of it is that if x e is equal to 0 is attained, then the system will continue to have the same value of the dynamical variable forever in future. Okay. And let us see if that is the case. That in fact is the case, because when you draw the phase portrait, what you see is that the moment you reach here asymptotically to 0, the system continues to have a value 0. If you start with 0 itself, x e is equal to 0. When you start with 0 itself, you have dx by dt, this is equal to a times 0, which means 0, which means that the gradient is 0. So, therefore, the next value will also, so your gradient is 0, which means you are on a horizontal line. So, the next value of the dynamical variable will also be the same. So, that is the meaning of the equilibrium solution. Okay. And finally, the question is whether the equilibrium solution is a stable solution or not. Okay. So, stability of the equilibrium solution. Okay. So, the first step is to determine the equilibrium solution. Our system was dx by dt is equal to a x, and our equilibrium solution x e was 0. Now, the question is whether the solution x is equal to 0 is a stable solution or an unstable solution. The meaning of stable solution is that if I go further in time as time t increases, whether I am going to remain on the solution, equilibrium solution, or am I going to diverge away from the equilibrium solution. This is the meaning of stability. Let me repeat, if x e is equal to 0 is an equilibrium solution, then if the system diverges away from x is equal to 0 as time goes to infinity, then the solution is called unstable. If it remains there, then the system is called stable. So, can we assess this using the phase portrait? Well, we can draw the phase portraits here again. So, this is t, this is x, this is t, this is x, and the phase lines look like this. These are the phase lines. And what is the equilibrium solution? The equilibrium solution goes like this, that this is the equilibrium solution. This is the equilibrium solution, right? X is equal to 0, this is the equilibrium solution. So, therefore, in this case you see that the system is moving. So, schematically I can represent this, that this is the equilibrium solution here. For this particular case, the equilibrium solution is here. So, the solutions are moving away from x e is equal to 0. So, this is x e is equal to 0 and the solutions are moving away, the arrows point like this. The solutions never reach in this region, whereas in this region as time t tends to infinity, here the solutions are coming towards x is equal to 0, x is equal to 0. So, therefore, the system is unstable, the equilibrium solution x is equal to 0 is unstable here, and the system is stable here, the solution x is equal to 0 is a stable solution. So, therefore, what we learned today is that typical autonomous system, which is first order linear, can have bifurcation in it, the bifurcation parameter being a. So, for equation of the type dx by dt equal to a x, the system offers a bifurcation at a is equal to 0, and depending upon the magnitude, depending upon the sign of a, the system can have a very different fate. The dynamical variable can blow up to infinity when a is greater than 0, and the system will settle down to 0 when a is less than 0. These concepts have very interesting applications in process industries, and what we will do is that we will take up an example from heat transfer in tomorrow's lecture and develop thorough understanding of how we can apply the concept of dynamics as applied to linear first order autonomous systems to heat transfer problem. Thank you.